Welcome to our channel. Today we're diving into what happened to Mars's water as discovered by NASA researchers. That rusty red point of light in the night sky whispers tales of a wetter past. It's a cosmic detective story, folks. Mars transformed from a potentially habitable environment to a cold, arid desert. What forces stripped Mars of its water? The answers are complex and crucial. Imagine a young Mars, billions of years ago. Not a desolate landscape, but a world with flowing rivers and vast lakes. This isn't science fiction, it's what scientific evidence suggests. The water vanished over eons, leaving behind ghosts of its presence. So where did it all go? Did it escape into space? Did it retreat underground? Or is there another, more intricate story? We'll explore the leading theories and uncover the latest findings. It's a story of planetary evolution and the quest for knowledge. Buckle up for an interplanetary investigation. This will change the way you think about our celestial neighbor.
How do we suspect that Mars, now so dry, once had water? The universe tells stories if you know how to read them. Our rovers and orbiters are our translators. They've sent back astounding images and data, ancient riverbeds and channels carved by water. Geological features point to sustained water action. Think of the Grand Canyon, but on Mars. It's written in the rocks and sediment layers. Deltas, like those on Earth, found on Mars. Jezero crater is a prime example. Water pooled, forming lakes for millions of years. Imagine standing on a Martian lakeshore billions of years ago.
Alright, so we've established Mars was likely a wet world. The evidence is compelling. But if it had all that water, rivers, lakes, maybe even oceans, where did it all go? This is where the detective work really heats up, and several prime suspects, or rather theories, emerge. One of the long-standing ideas is that a significant portion of Mars's water was simply lost to space. You see, planets, especially smaller ones like Mars with weaker gravity, are constantly battling to hold on to their atmospheres, and by extension, their water. It's a cosmic tug-of-war. And Mars, it seems, was not a very good contender in the long run. How does a planet lose its water to the void? Well, water molecules, H2O, in the upper atmosphere can be broken apart by ultraviolet radiation from the sun. The hydrogen, being very light, can then escape Mars's gravitational pull relatively easily.
Chapter 3. The thinning veil Mars' atmospheric demise and its watery consequences. Now, you can't talk about water on a planet's surface without talking about its atmosphere. An atmosphere is like a planetary blanket. It provides pressure, which is crucial for liquid water to exist, and it offers protection. Early Mars, we believe, had a much thicker atmosphere than it does today. This denser blanket would have allowed liquid water to be stable on the surface, preventing it from immediately boiling away or freezing solid. So, what happened to this protective atmospheric layer? Why did it thin out so dramatically, transforming Mars into the cold, low-pressure desert we see? This is a critical piece of the water loss puzzle. One of the leading culprits in the demise of Mars' atmosphere is the loss of its global magnetic field. Earth has a strong magnetic field generated by its molten iron core, which acts like a shield, deflecting the solar wind, a constant stream of charged particles from the sun. Mars, being smaller, cooled down faster. Its core likely solidified, or at least changed its convective patterns, causing its planetary dynamo to shut down billions of years ago.
Chapter 4. NASA's new clues MAVEN, Perseverance, and the Shifting Paradigm. NASA's missions provide fresh data, challenging old assumptions. MAVEN studies Mars's upper atmosphere and its interaction with the solar wind. It measures the rate of atmospheric loss to space. Solar storms increase this loss dramatically. MAVEN's data helps estimate Mars's atmospheric loss over billions of years. But atmospheric escape isn't the only factor. Water might be sequestered in Mars's crust. If not in the atmosphere, water must be somewhere on or in Mars.
Chapter 5. The future of the red planet, water, life, and human exploration. Understanding Mars' water history has profound implications for exploration and the search for life. Life requires water. Subsurface water could support microbial ecosystems. Missions like the ExoMars rover are critical. We're looking for preserved oases, hidden reservoirs of a water-rich world.
So the tale of Mars water is far from over. What we've learned, especially through NASA's dedicated research, is that the story is more complex and frankly more fascinating than we might have initially imagined. It's not just a simple case of water disappearing into space. It's a story of planetary transformation, of water becoming part of the very rock of Mars itself. This understanding reshapes our search for ancient life and informs our plans for future human expeditions. The red planet, though seemingly barren, still holds vast quantities of water locked away in its crust and ice caps, a testament to its once wetter, more dynamic past. The universe is a place of constant change, and Mars is a prime example of how planetary environments can evolve dramatically over cosmic timescales. Each new piece of data, each rover's discovery, each orbiter's observation adds another layer to our understanding. It's a testament to human curiosity and our unyielding drive to explore, to push the boundaries of knowledge, and to seek answers to the biggest questions. Are we alone? What is our place in the cosmos? Mars, our celestial neighbor, offers tantalizing clues.